So much drama in the LBC. It's kind of hard being Snoop D-O double G, but I somehow, some way keep coming up with funky ass shit like every single day.
Alrighty, here's the first problem. We're going to find the general solution to this ODE here. So we have y double prime that is, plus 5y prime plus 6y is equal to 0. So let's translate this into the characteristic equations. That would be lambda squared plus 5 lambda plus 6 is equal to 0. Now we're just going to find the roots, so we can actually just factor this. We don't have to use the quadratic formula, only if you want to, and only if it's necessary, right? So we could have lambda plus 2 and lambda plus 3, okay, is equal to 0. So our first lambda, lambda sub 1, could be negative 3, and our second lambda could be our negative 2. Okay, so now we can form our fundamental set of solutions. Y sub 1 is equal to e to the lambda 1, so that would be negative 3 times t. And then y sub 2 is equal to e to the lambda 2t, which is negative 2t here. Okay, so this is our fundamental set, and we can form our general solution by just sticking constants in front and adding those together. So I'll just use a and b for our constants. So a times e to the negative 3t plus b times e to the negative 2t, and there it is. That's our general solution to this equation here. And we actually, let me identify these. These both, negative 3 and negative 2, are both real numbers, right? And they're two distinct ones. So this is the case where we actually, if we would have plugged it into the quadratic formula, we would have gotten that the discriminant, this p squared minus 4q, is greater than 0. Thus, we have two distinct real roots. Real roots, okay? So that was the case for this problem here. Okay, number 2 asks us again to find the general solution. This time our ODE is y double prime plus y is equal to 0. So when we translate that into the characteristic equation, we get lambda squared, and then plus, and this is actually just a 1 here, this is like our q, okay, is equal to 0. So when we solve for this, we get lambda squared is equal to negative 1. So when we take the square root of that, we just get lambda is equal to plus or minus I, okay? So this is like a 0 plus or minus 1i. So that means our a is equal to 0 for the complex number, right? And our b is equal to a 1. Alrighty, so we can form our fundamental set by saying that y sub 1 of t is equal to e to the at, so e to the 0t, times cosine of bt. So that would be 1 times t here. And then our y sub 2 of t is going to be e to the at, so a 0t, times sine of bt. So that would be our negative 1t here. So this is equal to, the e to the 0 just are 1s. So this is a cosine t, and the bottom one's a sine t. Okay, so we can form our general solution just by putting constants in front and adding them together, so by forming that linear combination, right? So a times cosine t plus b times sine t. That is our general solution here. And the case that we got, because we had our complex numbers, this is the two distinct complex roots case. Okay, complex roots. Which means that if we were to have done the quadratic formula and everything, we would have gotten that p squared minus 4q is less than 0. And because the discriminant is less than 0, we would have taken the square root of a negative number. Thus, that's how we got our imaginary numbers and our complex roots and everything like that.
With my mind on my money and my money on my mind.